Okay, this video is about the history of atomic theory. The first person to come up with an atomic explanation for the state, like the nature of matter, was a Greek philosopher named Democritus about 2,500 years ago. Basically, he argued that there was a certain smallest thing that was no longer divisible. So if you kept cutting matter into smaller and smaller pieces, there had to be something that was the tiniest. Most people didn't care for it, and they basically thought that matter would be indivisible forever, so you could cut something up into an infinite number of pieces. John Dalton was really the first guy who came up with a modern theory for modern atomic theory. So basically what he observed was that compounds form in whole number ratios. It's always the same whole number ratio, no matter what no matter what two things you are combining. So you're never going to have H2.50, it's always going to be H2O. It has to be a whole number of atoms combining to form a compound. So because of that, he hypothesized that atoms were basically like a billiard ball, and you'd have some, like this one would be a fluorine atom, this would be a hydrogen atom. How do I know what type they are? Because they each have one hole. Something like carbon would have a different number of holes, and then these would fit together, like the molecular molecule kits that we use. And it's a good approximation, but it's not really what's going on inside the atoms. So after Dalton came J.J. Thomson. So J.J. Thomson is in the latter half of the 18th century. And what he does is he discovers the first subatomic particle that anyone had known about. Now, they knew about electricity, and he discovers the electron. So no one knew what was moving around when electricity flowed. He was the first person to discover that. And what he did was he had a tube that he hooked up to a battery on either side. And then a weird thing would happen. So inside this tube, he had it evacuated. So by that I mean there was very little gas in between. And what he got was this weird, like, ray going across. So, like, this line of just charged particles would basically cause the gas in between to light up. And then he went a step further, and he put another set of charged plates here. So a positive and a negative. And when he did that, he found out that it actually deflect the beam and make it move up towards that positive plate. So he goes, hey, this must be a negative particle. And this negative particle has to come out of the atom. So what he said was, you know what? Atoms have to have some smaller bit to them. So basically, you've got this large positive area, and then dotted on the inside are electrons. And it was these electrons that he saw flowing through the gas and being deflected by the plate. This is called the plum pudding model because, like, you've got this blob, which is the pudding itself, and then these are stuck in there like plums in a pudding. Not like a Jello type pudding, though. The next guy, so one of Thomson's students, Ernest Rutherford, comes along, and he wants to probe the plum pudding, and radioactive nuclei were recently discovered. What he does is he goes and he discovers the nucleus. So before Rutherford, the structure of the atom was it wasn't really understood at all. So here's what Rutherford's apparatus looked like very briefly. Real quick, we have a radioactive chunk of metal here. So this is what we call an alpha emitter. It's going to shoot out alpha particles in all directions. But it's inside this lead box with a hole. So the lead box with the hole stops all of them but what goes through the hole. Now that's important because basically what we've done is we've made a ray now of positive helium particles. So these are charged helium nuclei that are flying through the air, and they're hitting this gold plate here. Well, actually, it's a piece of gold foil. The reason why we use gold foil is because you can pound it unbelievably thin. So his gold foil was only about 10 atoms thick. It's very, very thin. And so what happens is these helium particles, which are positive, if they get close to an atom, they get deflected. But most of the time, they just go right through. So every once in a while, though, one gets close to the nucleus, and it gets deflected. And then it hits this detector here on the outside. This detector makes a flash whenever something hits it, so it phosphoresces, it scintillates. So by figuring out how often it's hitting at all these different angles, Rutherford is able to deduce the size of his atom. Even cooler is they move this detector around because they notice it's hitting all the way out to the edge. Well, maybe we should move the detector out over here. Do we still detect some? And yeah, some get bounced back like that. And some get bounced back almost 180 degrees. Now, Rutherford said this would be like firing a cannon at a piece of tissue paper and having the cannonball bounce back at you. And that's true. You shouldn't be able to do that. But that's only if you think about the plum pudding model. Because in the plum pudding model, if we go back here, since it's this big area, it's not at all concentrated, these helium atoms, or these helium nuclei, would just go straight through. They would maybe get deflected a little bit, but they wouldn't be able to be deflected nearly as much. So what Rutherford finds, what he really finds, is that you have a small positive area, and if you got another positive coming towards it, that is going to get deflected back almost 180 degrees. And, it's very rare because the size of this nucleus is very, very small. But Rutherford was able to pretty well estimate how small that radius was. So he comes up with what's called the planetary model. And the planetary model basically has the nucleus as the sun, and then you have electrons orbiting around it. There's one problem with the planetary model, and that's that anytime you have a accelerating charge, anything moving in a circle has to accelerate. To keep moving in a circle, it would actually lose energy. So this would radiate away basically light energy, and then it would, since it's losing energy, it would spiral into the center of the atom. And when you worked out the numbers, it turned out that basically no atom would be stable. That atoms would only last a few, millionths of a second.